the tablet dosage form, several quality control parameters you have to test, just like of your weight variation test, disintegration test, then hardness, friability, and most important thing is that in vitro dissolution study. In vitro dissolution study means why we perform these things. In vitro dissolution study to check the drug release from the dosage form, that is the tablet, whether it releases the drug as per our wish or not. Understood my point? That is, if I prepared one tablet for 12-hour duration, it will give the release of the drug up to 12 hours. That means whenever we go to the in vitro dissolution study, so we check that whether the drug is released from this system up to the 12 hours or not. So it is very, very important parameter to check. So in my left hand side, this is the example of one paddle type instrument, USB paddle type. Here we perform the in vitro dissolution study. Now, suppose we get the whatever release we want, we get this from the in vitro study. Now we can't say that whenever this same tablet we are taking orally, it will behave whatever I got from the in vitro release. It may change because there are several physiological factors placed in that. So whenever we are taking the tablet inside, then several factors will come, and accordingly the drug will release from the dosage form. Understood? This study is called as the in vivo study. Clear? So in vitro and in vivo correlation, it is nothing but it is a bridge. We have to check, we have to correlate the in vitro data with the in vivo performance of the drug. Understood? Okay. Joseph, sir, it is second slide is visible.
Yes, sir. Yes, sir. It's a why IVIVC, sir.
Yes, yes, yes. Now the question is that why this IVIVC is required? Basically, there are several factors are there to check, or importance you can say that, to check the IVIVC. Among them, I can broadly explain here about the two importance, that is the bioavailability, bioequivalence point of view. This IVIVC is required, and second one is the regulatory aspect. This point of view, this IVIVC is required. In bioavailability point of view, we know that bioavailability means the rate and extent at which the drug molecule enter into the systemic circulation in unchanged form. This is most important term, that is the unchanged form. If the drug becomes changed before taking entry into the systemic circulation, we can't say that it is 100% bioavailability we can't get, we can achieve. Yes, the 100% bioavailability we can achieve only by the IV dose, because we are directly injecting the drug into the systemic circulation. But if you go to the oral dosage form, as I discussed in the early slide, that when we are taking this drug, dosage form, suppose tablet, it first reaches the different portion of your GI tract. First, it comes into the stomach. Here the environment is the acidic in nature, then it will gradually comes into your intestine, that is small intestine and large intestine. So there the environment is totally different. It is a basic pH zone. And this GI lumen, just you see in the left, this figure, this GI lumen means intact GI tract I am discussing. Here, different types of enzymes are also present. That is called as a gut enzyme or GI wall enzyme. Specifically, the cytochrome, this category of enzymes are present. These enzymes digest the drug molecule, the parent drug. That means here some portion of the parent drug becomes metabolized. That means it changes. And from this GI lumen, it is not directly enter into the systemic circulation. Before taking entry into the systemic circulation, it first enter into the portal vein to reach into the liver. As we know that the liver is a bank of several types of enzymes. Here the main metabolism is taking place. You already know that the metabolism phase 1, phase 2, this metabolism different phases are there. This metabolism is taking place into the liver. That means here also some loss of parent drug is taking place. As a result, ultimately from liver, when it enters into the systemic circulation, so one portion of the parent drug gets metabolized. That means it changes its property. So that is why this, whenever you are taking one drug orally, you can't get the 100% bioavailability. So in that point of view, this IV-IVC is important. And regarding this regulatory aspect, so you know that one term, that is the clinical trials. So whenever you develop one formulation, it should pass the clinical trial phases. So before clinical trials means study on human being. So before study on the human being, it should be studied on the animals, different animal models. Maybe it may be rat, it may be mice, it may be rabbit, it may be guinea pig, it may be dog, it may be monkey. So several these animal models we should use before entering into the clinical trials. So this study on the drug on animal model, it is called as the preclinical studies. So if your dosage form pass the preclinical study, all the data you have to submit to the IRB, that is the Institutional Review Board, to get the permission to conduct the clinical trials. If the data satisfied this IRB, they give you the permission to conduct the clinical trials, that is the human volunteer. So whenever you start your clinical trial process, it is a time consuming matter, obviously. Another thing is that after this clinical trial phases, you have to again submit all the data to the FDA or EMA, this type of approval bodies. You have to submit your clinical trials data to them. If this data is satisfied, then they will give the approval. That is the regulatory, called as the regulatory approval of that dosage form. That means in these 2 point of view, this IVIVC is very, very important. Understood? Any queries up to that? Any queries? Okay. So now come to the how we can establish the IVIVC. That means in vitro in vivo correlation. How we can perform this? So there is basically 2 approaches we can follow. One is the convolution approach. Another one is the deconvolution approach. Is it visible, Joseph sir? This slide?
Yes, sir. Yes, sir. It's visible, sir.
Okay, okay. Thank you. So I discussed these 2 approaches, the differences between these 2 approaches by these 3 figures. In the left hand figure, just you see, it is a typical plasma drug concentration time profile. Just you see from where we get this type of graph. It is a Gaussian type of graph, bell-shaped graph. So this graph we can get when we are taking the drug orally, means in vivo study. In this phase, just you see, in the steep rise portion, this portion, it is called as the absorption phase. That means absorption, we know that it is a entry of the drug into the systemic circulation from the site of action in the unchanged form. That means in the first phase, that is the absorption phase, rate of absorption is much more higher than the rate of elimination. Elimination means we know that the pharmacokinetic, this process, we can divide into 4 phases. One is the absorption phase, second one is the distribution phase, third one is the metabolism phase, and fourth one is the excretion phase. So elimination means metabolism and excretion. Both 2 phases are called as the elimination phase. So in the absorption phase, here the rate of absorption is much more higher than the rate of elimination. One time will come when this rate of absorption is become equals to the rate of elimination. So here you can get one plateau form. This indicates the Cmax value. Cmax means maximum concentration. The concentration of the drug in the blood is maximum. And corresponding time where you can get the Cmax value, this corresponding time, we can say that it is a Tmax, that is time to reach the maximum concentration of the drug in the blood. So after this plateau phase, this elimination phase is mainly there. The first phase of this graph, just you see in the right hand portion, it is the post-absorption phase. This post-absorption phase means here the rate of absorption is little bit lesser than the rate of elimination. And the lower portion of this line, here it is written the elimination phase, where the rate of absorption is very negligible than the rate of elimination. So this graph you can get when you are taking the drug orally, and it is basically it is a in vivo absorption graph, you can say that. In vivo process, after this in vivo process, you can get this type of graph. And in case just you see in the right hand side, two graphs are there. In the above graph, it shows the elimination phase, completely elimination phase you can get. Just you see Cmax here, and from there it is the gradually decreasing. This indicates the elimination phase only. And in the lower portion, just you graph, second graph, you just see that here two types of indication is there. One is the bold line. This bold line, as you already performed in your lab, that is the in vitro dissolution study, you can get this type of bold line graph, is it not? That indicates the absorption phase. Understood? That is the percent dissolve, or you can say that cumulative percent of drug release versus time. You can get this type of bold line graph. And here you just see some dotted line are also I am representing over here. That indicate that is the multiple doses form. That means in a disease, whenever we visit our doctor, they have suggested that one tablet you have to take 3 times a day or 2 times a day, whatever may be. That means if it is a 2 times a day, we are taking generally 12 hours interval. So from whenever you take the first dose, just you see this dotted line will come here, and this portion, that is the post absorption phase, when it will reach, suppose here the 12 hours is there, again you have to take another dose. So in that manner, the steady state concentration we can achieve. So in the first case, you just see that when you take the first dose, it will reach the Cmax value. Again, it will drop down. At that point, you are taking another dose. But the amount of the drug which you have taken in the first dose, it also remains in our body. That means this portion, this lower level dotted, this portion is already also present in our body. That is called as the accumulation of the drug. Understood? So, if you understand these three graphs, then it is very easy approach and deconvolution approach. Just you in vitro dissolution study you already performed. When you let data with this in vitro data, then this IVIVC called as the deconvolution technique or approach. Understood? But in case of convolution approach, only you need this dissolution, in vitro dissolution data. When using this in vitro dissolution data, when you get this in vivo performance of the dosage form, then it is called as convolution approach. Clear this? From in vitro drug release profile, when you convert these things into in vivo performance by suitable pharmacokinetic data, then it is called as the convolution approach to establish IVIVC. It is very simple thing, simplest method to establish the in vivo performance. If you go to the deconvolution approach, that means you have to feed the dosage form into human volunteer. It requires several ethical permission. All these formalities you have to follow, and it is also a time-taking process. Is it not? Clear these things. So my today I will just go to the discuss about the convolution approach to determine or establish the IVIVC. For this convolution approach, you need only three pharmacokinetic parameters. That is oral bioavailability, that is indicated by the F, because we know that the bioavailability is two types. One is the absolute bioavailability, another one is the relative bioavailability. So we just concentrate on the absolute bioavailability, that is the fraction of the drug which is available in the systemic circulation. That is why it is denoted by the F. Second one, it is apparent volume of distribution. Joseph sir, it is visible, this slide 4. Can you see the slide 4? Joseph sir. Hello.
Am I audible, sir?
Is it visible?
Yes, sir, it's visible, sir.
Slide 4.
Yes, sir.
Actually, my network issue is there. That is why it is. I am just confirming whether it is visible or not.
Yes, clearly visible, sir.
Okay. So, second pharmacokinetic parameters is the apparent volume of distribution. Hope the BPharm students and the MPharm master students, they already know that the apparent volume of distribution, what does it mean? That means what actually? Whenever the drug reaches into the systemic circulation, that is in the blood, immediately the drug molecule distributed throughout our body system. Wherever the blood is flowing, the drug also going over there. Is it not? This is called as the distribution. And we know that our approximately our total volume of the fluid is nearly 25 liters. It consists of the extracellular fluid, intracellular fluid, blood, all these things. So it is also important pharmacokinetic parameters, that is the apparent volume of distribution. That is the per kg, how much volume of the means the drug is going into our whole body. And another one is the elimination half-life. We know that it is denoted by the T half. That is the time taken to becomes the half the initial concentration of the drug. It is called as the elimination half-life. The oral bioavailability, apparent volume of distribution, elimination half-life, all these pharmacokinetic parameters of a particular drug, you can get it from the standard book. It is written over there. Basically, you can follow the Goodman-Gilman, this book. In the last appendix pages, you can get these pharmacokinetic parameters of the so many drugs. And obviously, the good pharmacology book, it is also written. Understood? So, by these three pharmacokinetic parameters, we can convert the in vitro dissolution data into the in vivo performance. We can predict the in vivo performance of that particular dosage form. Understood these things? So now I share my one work, and I want to share my Excel sheet to describe how you can calculate this to get the in vivo performance. Okay. So is it visible, the Excel sheet?
No, sir, it's not visible, sir.
It is not. Now
Yes, sir, now it's visible.
it is visible, no, Excel sheet. So up to that, it is clear. Everybody, just you ask